This video will discuss electron configuration for atoms. So this video is going to be exactly identical to the same lecture you would have gotten in a general chemistry course, but we've reached the part of P-Chem where we've actually developed all the mathematical infrastructure to have derived all of these expressions through rigorous quantum mechanics. So the course up to this point is really the explanation of why the electron configurations look the way that they do and what the energies are. And we're reaching the same conclusion that you were just flat out told in Gen Chem. So typically professors do expect these types of things on test, and it should basically be the closest thing to free points that you're going to get in this course. So definitely take care to review it so where you don't make some silly mistake. But yes, this is the same thing as it is from Gen Chem. So starting off with the hydrogen atom. Hydrogen atom has a configuration of 1s1 for its single electron, or we could, in terms of spin orbitals, say 1s alpha. There's a single spin up electron in the 1s orbital. For helium, we have 1s2, so 1s alpha, 1s beta, a single spin up and a single spin down electron in the 1s orbital. So anytime we have a 2 here, we're going to say there's a spin up and a spin down electron in that orbital. 1, there's just going to be a spin up. And we can also say that this 1s2 is a bracket helium. So whenever we have these brackets, that's saying whatever happens before this bracket is just the configuration of that noble gas. So noble gases like helium, neon, argon, krypton, xenon, just being things that have completely filled valence shells. That we say, if we know those, it's everything beyond that. Okay, lithium is 1s2, 2s1 for its 3 electrons, or helium 2s1. Beryllium 1s2, 2s2, helium 2s2. Boron 1s2, 2s2, 2p1, or helium 2s2, 2p1. Notice that we filled the 2s shell before the 2p shell. So the 2s shell in a hydrogen atom is equivalent in energy to the 2p shell. But we're not in a hydrogen anymore. There are multiple electrons here. So the relative ordering of the energy levels of all these atomic orbital subshells all depends on, number 1, the energy of the hydrogen atom, and number 2, how well each of them is shielded from the nucleus. So if you look back in the video on radial distribution plots of the hydrogen atomic orbitals, you'll see that 2s and 2p have a different shape for what their electron density versus radius is. So the 2s actually has some density that's closer to the nucleus on average than the 2p, which is why it gets shielded less and has a lower energy and thus gets occupied first relative to 2p. So we continue that down the 2p block all the way up to neon, 1s2, 2s2, 2p6. If I go all the way to aluminum, that would be 1s2, 2s2, 2p6, 3s2, 3p1, or neon, 3s2, 3p1. If I go all the way to zinc, that would be argon, 3s2. Sorry, this should be argon 3s2. Sorry, it should be argon 4s2, 3d10. Much better. As I said, take care to make sure that you're not making a silly mistake in general chemistry level material. So the interesting thing to note there is that the 4s orbital gets filled before the 3d orbitals. So again, that's because the 4s has electron density closer on average to the core and gets shielded much less than the 3d, which gets pushed up to a higher energy. So the order in which these atomic orbital subshells get filled, in case you forget, can be built by this kind of triangle here. So at 1s, at n equals 1, you only have L equals 0, or S. N equals 2, you have S and P, L equals 0 and 1. 3 has SPD, 4 has SPDF, etc., GHI as it goes. And you start at the top right, and you draw an arrow going down the diagonal. So you fill 1s first, 2s, 2p then 3s, 3p 4s, 3d 4p 5s, and you go all the way down until you get to however many electrons your atom of interest has. So as I was mentioning there, these get filled up in the order of what's lowest energy first. The 2s has less shielding, more attracted to the nucleus, so it's lower in energy than 2p. The 4s has so little shielding that it actually goes below energy than the 3d. And as we can see there, that 6s is below 4f, and lots of things happen beyond that that are exceptions to that. So these are the electron configurations. You represent the noble gas configurations in brackets. Each orbital is assumed to have spin up and spin down electrons whenever we have two or multiple in there. And we fill them in this order, which is consistent with how we go across the periodic table, giving the periodic table its shape.